Hi, my name is Amani Siddiqui, and this is my Lab 5 for Faraday's Law. To quickly go over some of our objectives, so our main purpose for this lab was to collect data on a magnet falling through an aluminum tube in order to observe and apply Faraday's Law. So just to give you a quick overview of the results I got, for the experimental time, I got an average of 1.25 seconds, and for the computational time through the glow script simulation, I got 1.118 seconds. To quickly go over some of the fundamentals, the main fundamentals I used to calculate this experiment was Faraday's law, Byers-Savart law, Newton's second law, and Newton's third law, Ohm's law, the magnetic force on a loop, and the time derivative of a magnetic flux of a dipole. I listed some of the formulas on the side so you can easily see how they're represented. Some assumptions we made for this lab was that air resistance acting on the falling magnet is negligible, and gravity and the magnetic force from the aluminum tube are the only forces acting on the falling magnet. As for the actual experiments, for the models, the magnet was used to model a magnetic dipole while the aluminum foil modeled a tube through which it fell. For the system, I classified this as the aluminum tube and the magnet, and as for the surroundings, it was all other external factors. As for the procedure, I just aligned the meter stick at a given length in order to find the distance dropped, and I used my phone to record and take a video and then calculate the velocity based off when it fell onto the table. And I did this for 5 different trials. In the next slide, you'll see a representation of this. So we have 2 videos here. The one on the right that's playing right now is the one where we used it without the aluminum tube, and I'm about to play the one with the aluminum tube.
Awesome.
As observed, we can see it kind of took longer, and as I said earlier, the average for the aluminum tube was for 1.25 seconds, while the one for the right-hand side was around 1.5 seconds. So these are just throughout my trials, the different times I've gotten, and we had some given values, which you can see in the bottom left-hand corner. Now it's time to get into the glow script model. Here we initialize our parameters. So moving on to the simulation of this experiment using glow script, in these first few lines, we more so just defined our physical constants as well as the graph. And now here's where things get a little more complicated. We first initialized our initial parameters I had listed on the slides with the constants such as mass, length, etc. In these following lines of code, we also created the aluminum tube and the bar magnet model. After this, we defined functions for both magnetic field due to the dipole, or in our case the magnet, and we created a function for the magnetic flux created by the bar magnet. Then we proceed to calculate the gravitational force on the magnet and the magnetic flux on a ring due to the falling magnet. Then in step 5 and 6, we calculated the magnetic force on the aluminum tube and then the magnetic force of the aluminum tube on the magnet. Finally, the net force is calculated by adding the gravitational force and the magnetic force using superposition, and the position of the magnet were calculated using Newton's second law. And this is where the graph is created. In the top left, we can see the representation of the magnet, the red ring representing the North Pole, and the blue magnet, or the blue representing the South Pole. On the right, we can see the outputted graph. So as we can see, the average time in person took longer than the average time calculated through the simulation. And well, in our case, it could have been that the magnet could have been in not an ideal state, meaning that since it had been used prior from a lot of other students, it could have possibly been chipped, broken, or simply not as powerful, which is why it would have taken longer to draw. So discussion questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the following magnet change? Well, if the resistivity of the conductor were reduced, that means that the current may be a bit stronger, which in theory means that the magnet may be able to float in the middle of the tube, which is silly to think about, but it's because the induced current would be equal to the dipolar strength. Unfortunately, this is unlikely because it's basically impossible to have something with 0 resistance. As for the second question, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? It would just practically change the fact that it would be inconsistent, so it's more likely to just fall off to the sides a bit more. Thank you very much.